In this, the second part of the trilogy, I will explain why the difference between relative and absolute time at different locations in space can mitigate the need for the elusive dark matter, and why the Hubble sphere is our future horizon of causality, and why cosmic data from the early universe fit so well with Allan Guth's inflationary theory. In the first of this trilogy, I show that a day for the Earth and this satellite is a universal absolute time displacement, while clocks measure the relative duration, indicating a difference between absolute displacement and relative duration, where absolute time preserves ordinality and position, and relative emergent duration is how we age and measure speed and distance. And light always travels from the past to the present, giving us the electromagnetic arrow of time. The now moment is always changing, indicating a cosmological arrow of time. The speed of light is constant at any now moment, but our light speed rulers are shrinking over time. We experience time as a duration. Relative time is another time dimension, depicting how fast we are travelling through absolute time. Like a speedo in a car, the Hubble parameter tells us how fast relative to the rest of the universe. Faster clocks produce a slower Hubble constant, and slower clocks in a gravity well produce a faster Hubble constant. The matter is shrinking relative to the past. The rate of change is inversely proportionate to the expansion of space. The Earth is shrinking by about 1 millimeter a year to equal the Hubble constant of 70 kilometers per second per megaparsec. The satellite is relatively closer, yet remains the same distance. Gravity-bound systems like a galaxy shrink with the matter in the same way. The faster the clock on the satellite makes the orbital speed slower relative to the Earth by 45 microseconds a day, but the satellite is only 20 light seconds away, whereas a star at the edge of a galaxy like ours could be 50,000 light years from the center of a galaxy and could be traveling orders of magnitude slower than what we might measure it, as the speeds we see are relative to our relative time in our relative reference frame. Could this be the nature of dark matter? If the emergent space-time curvature were overall monotonic between the edge and the center of a galaxy, it would modify the apparent rotational curve to be more Newtonian in its nature. Orbital speeds are relative to the clock of the observed. The relative clock time of the outer stars in this galaxy will be ticking faster, so their emergent orbital speed is slower than stars that are deeper in the gravity well, even though they appear almost synchronous. Travelling at 186,000 miles every second, it takes light 3,300,000 years to cover a megaparsec. A sphere this big contains about 40 galaxies. With every increase in megaparsec, the apparent recessional velocity increases. The scale changes, the matter shrinks. In the expanding space model, light gets stretched as space physically moves the distant galaxies. With a time parameter model, the light has the same frequency as when it left the galaxy. And then when we measure it with our smaller light speed rulers, we see an apparent redshift. The difference is just a matter of scale change. When the light from this very distant galaxy was emitted, the wavelength was double that of today, and a relative second displays twice as much absolute time. We can use this equation to determine the distance of a galaxy relative to our scale. Z is a difference in wavelength between the past and the present scale. So in this far-off galaxy, Z would equal 1. When we rationalize the units, we can then calculate the distance of 14 billion light years. You may think that that is the age of the universe. That is because the lambda cold dark matter model uses 1 divided by the Hubble constant to get an age, that is based on the galaxies actually moving, which in this model they are not. Then extrapolating back to t equals 0, doing so means they have to modify this equation to account for the co-moving distances and get an age that is too young for the universe that we now observe.
So a galaxy at Z1 will be 14 billion light years away and 14 billion years old, with an apparent recessional velocity as fast as light. This we call the Hubble sphere, a distance and speed relative to our present changing scale and not a real absolute movement through space.
Paul Dirac, a famous physicist, made the observation that related the ratios of size scales in the universe to that of the force scales. The ratios constitute very large dimensionless numbers. The strength of gravity, as represented by the gravitational constant, is inversely proportional to the age of the universe, while the mass of the universe is proportional to the square of the universe's age. He was convinced that this implied a cosmology with these unusual features. However, it conflates the age of the universe with the age at the Hubble sphere, which is also a constant as our time-dependent light speed rulers shrink over cosmic evolution. Although this is essentially a static model, the changing distances have a kind of reality. Like this Alice in Wonderland analogy, the key does not move, but when she shrinks, she can no longer reach the key. And although we see things that we were in causal contact with when the light left, if they are now beyond our Hubble sphere, our light now will no longer reach them. The distance to the Hubble sphere is a constant at Z1, but the position is not. The Hubble sphere is positionally shrinking with our atomic time-based rulers, and like these rulers, the constants of nature evolve over cosmological time while staying constant in their measurements of both time and distance. Our light cannot reach a superluminal galaxy, and so the Hubble sphere is our future horizon of causality. We can see beyond our Hubble sphere, for that light is in our present. Our position was inside their horizon of causality when their light left. Gravitational waves travel at the speed of light, which means that the Hubble sphere is also a limit to our gravitational influence. At a great distance, the influence of our gravity is diminishing. This means, in the past, the influence of gravity had a much larger range and a reason why such enormous structures could have formed long before any stars or galaxies. This is the largest structure that we know of and is approximately 10 billion light years long. And because our atoms take up less space over time, gravity gets stronger locally, while the gravitational constant remains a constant. This means gravity could have been weaker on the surface of the Earth in the distant past, and a possible reason why such colossal creatures were able to exist in the past on land and in the air. This model contradicts this paper by Davis and Lineweaver, Expanding Confusions, where the reason we can see galaxies beyond the Hubble sphere is that although the galaxy is moving away from us faster than the speed of light, the light from the galaxy is heading towards us in space that is still moving away from us faster than light. Until that is, the Hubble sphere expands and sends the light back towards us. Let us now think about that. If we are in an expanding universe that is speeding up, the Hubble sphere must be shrinking. For instance, if the grey car takes 20 seconds to get to 60 miles an hour, and the red one only takes 10, the faster one gets to 60 in less distance, not more. Accelerate the grey car faster and it would get to the specific speed faster. And if the universe expansion is accelerating ever faster, then the Hubble sphere will be shrinking, not expanding. When Earth moves away from Jupiter, Io's orbit appears to slow down. Ole Römer figured that the perturbations in Io's orbit were due to light having a finite speed, and was the first to calculate the speed of light from the time difference between opposition and conjunction. And if the galaxies did have a real movement due to the expansion, then if we have 4 identical galaxies at ever greater distances from the observer, all rotating like this one, then this one would appear to rotate slower because it is moving away faster. The third one on the Hubble sphere will appear stationary as it is moving away at the speed of light. Then commoving distances would mean that the fourth one would appear to be rotating in reverse, as the light has to change time direction at the Hubble sphere, and we do not see occurrences beyond the Hubble sphere in reverse time order. If we were here, and this is a galaxy at Z1 on our Hubble sphere, and then we were to borrow the TARDIS to travel back in space and time to when the light leaves that galaxy, you can see that the position of our home galaxy is well within our new Hubble sphere. Even if we move further back in space and time to this superluminal galaxy, home is still within our horizon of future causality, and the reason we can still see it now. The distance to redshift is relative to time and distance at our current scale. Travel back in space and time to here, and for every 1 second of today's seconds, 2 seconds will pass here, and 4 seconds here, and then 8 and 16, and so on. The experience of time does not change, but compared to time now, clocks would be much faster. Beyond the cosmic microwave background and the limit of our visible horizon, clocks would tick exponentially faster, which is why inflation theory fits so well with the data. The apparent expansion was only fast relative to time now, and would not have seemed that way in the past. Apparent inflation now has a reason. Travel all the way back to the cosmic microwave background, and you would be in an infinite ball of primordial plasma, and for every second today 36 minutes would pass. You would not see a second hand going around 36 times a second. It would appear normal, like this one. In the last part of this presentation trilogy, I will explain the nature of Big Bang, why the matter and antimatter imbalance never annihilated one another, and why this interpretation of the Big Bang itself can adhere to the principle of sufficient reason. And thank you again for following me down the rabbit hole of cosmology. We still have a way to fall.